Let's take a look at chapter 5. Get started on this chapter, not chapters, chapter 5. We finally talk about integral calculus. So what are our sections here? Okay. The first two sections are really just there to build up to 5.3. So Riemann sums, which we'll talk about now, and the definite integral, defining the definite integral, those are going to serve as stepping stones to where we really want to be, is 5.3 in the fundamental theorem of calculus. Once we have the fundamental theorem of calculus, you know, it's kind of like back in chapter 2 when we were developing the idea of the limit, and the whole purpose was so that we could get to the definition of the derivative. Then once we had the definition of the derivative, we quickly found all of these derivative rules and these shortcut formulas for finding derivatives of things very quickly. We're basically doing that process again, but it's much shorter with integrals. Riemann sums and the definite integral lay the foundation, and then 5.3 we see, you know, the fast method with the fundamental theorem of calculus. Okay, once we have that, then 5.4, we're going to kind of expand our understanding of integrals with indefinite integrals and net change. Net change is like our first exposure to an application with integration. And then in 5.5, we're going to expand our powers further. We'll be able to perform integrals on more functions when we learn the substitution rule. Okay, but first things first, let's talk about Riemann sums. Actually, going all the way back to the beginning, what are we trying to do here with integrals? So imagine a function, maybe something like that will work pretty well. And imagine a starting and ending point, that function going, just looking at it from A to B. And then think about the area between that function and the x-axis. The idea is, what is that curved area? Can we find it? Can we calculate these things in general for any function? What is the exact area between f of x and the x-axis, starting at A and ending at B? Okay. We refer to that area is called the definite integral. All right, so it's kind of our goal that we're working towards right now. How do Riemann sums play into this? A Riemann sum, by the way, Riemann, German mathematician, a Riemann sum will approximate that curved area using the areas of rectangles. Okay, so in 5.1 with Riemann sums, we're like starting from scratch. We can pretty much forget everything that we've learned in this course so far, just for this one section anyway. We're not going to be performing any derivatives. We're not going to be looking at any anti-derivatives, starting from ground zero, if you will, starting from scratch. A Riemann sum will approximate that curved area using rectangular areas. What do we mean? What's that all about? Here's a little bit more detailed definition. A Riemann sum approximating the definite integral using equally spaced rectangles of n subintervals. We might perform a Riemann sum in a couple of different ways. So I'll first show you using left endpoints, and then in a moment using right endpoints. So again, we can imagine that curve, right f of x starting at A, ending at B. Okay, we're going to divide, just looking at the left endpoints, we're going to divide that region up into equally spaced regions. And eventually we're going to make rectangles out of them. So let's pick something easy. Let's divide that area up into 4 equally spaced regions. So I've got my 4 regions, this one, 2, 3, and 4. Okay. And you notice I label the left endpoint for each of my regions because we're doing the left sides. So for this first region here, I'm going to label the left side of it as X1. The second region, I'm going to label the left side as X2. The third region is X3, and the fourth region here is X4. We don't need to label the very last part because we've already thought about that region with X4. Okay. In each of those four regions, we're going to create a rectangle. Here's what those would look like. So for this first one, right, think about that left side. The left side determines the height of the rectangle. So we'll go up until we hit the function, and that's where we make our height. For the second region, we'll follow the left side up until we hit the function. That's where we make the height, and so on for the third and the fourth. Okay. Once we have our rectangles, then we're thinking, okay, what are the areas of those rectangles? So we can find each area, and then the idea is that we add them all together, and the sum of the areas of these rectangles will give us an approximation for that curved area. These rectangles were rather large, right? They left some big gaps. This last one hangs over a little bit and sort of kind of makes up for some of that other lack, but you know, that might be a decent approximation. All right, you got to start somewhere, right? Okay, finally, one last thing to mention. We said these are equally spaced rectangles. They all have the same width. We're going to call the width of the rectangle delta x. Delta might sound familiar, tells us like the change in x, delta x. So that same width would be true for all four of them. Okay. If we were to find a Riemann sum using left endpoints, we would call the sum of those areas, it'd be denoted L sub n. Here we used 4 subintervals, so we'd say L sub 4, left endpoints with 4 subintervals. Okay, examples will come in a moment. How about the right endpoints? Similar idea. We can divide that region up into equally spaced smaller regions. I'm going with 4 again. But now this time, each region we label the right side. So this first region is still here, but now we're labeling this edge its right side and continuing in that way for all 4 of them, x1, x2, x3, x4. Then we'll create the rectangles, but now this time using the right sides as their height. So the right side here, where it hits the function, that makes the height. For the second region, the right side, and so on for the third region, the fourth region. Again, you see a lot of these are overhanging, right? And that last one has that gap. Once we have our rectangles drawn, we're going to find the areas of each of those rectangles, add them all together. That will give us a different approximation for that same definite integral, that same curved area. Then we should mention, no, these are all equally spaced again. So we've got delta x for each of our 4. And this, if we're using right endpoints, we're going to denote that as R, capital R sub n. Okay. We've got left endpoints, right endpoints. There is one more option. You might use midpoints. It tends to be that midpoints would give the best approximation, although it's not always necessary or the fastest. Usually it will be the best. Let's see how this works. So we're going to divide our region again into 4. We're just using 4 here because it's convenient. We could divide it into as many different subintervals as we like. But okay, going with 4, we note where the midpoint of each of those 4 regions is. So there we've got x1, x2, x3, x4, all at the centers of their regions. That means we take the height of each rectangle from the center. So for x1, go straight up the center until you hit the function. That's where you make the height, like so. So we'll do that for each of our 4 regions. And as you can tell, yeah, that's probably going to be the best approximation typically. But okay, then we find the areas of those regions and we'll add them together. Of course, each one, they're all equally spaced. So they all have a width of delta X. And how do we denote it? Capital M sub n for the midpoints with n subintervals. Okay. Hopefully just the concept makes sense. How do we actually do an example? How do we actually perform this? Let's check out these two. Evaluate the Riemann sum. We're gonna do a right endpoint in part A and a midpoint in part B. So part A, we're gonna find R4 for f of x equals x squared plus 1 from 0 to 6. And part B, M5 for f of x equals x squared e to the negative x from 1 to 4. All right, let's do it. Got it all set up here. Evaluating the Riemann sum, we'll start with finding R4, the right endpoints with 4 subintervals for f of x equals x squared plus 1 from 0 to 6. Okay, you might think, do we need to sketch the graph of our function x squared plus 1, right, to draw these rectangles? No, don't need to do that. All we need to do is create like a little number line from where we're starting and ending from 0 to 6. 0 to 6. And then note how many subintervals, right? So we're doing 4 subintervals. So I can divide it in half and then in half again. I've got my 1, 2, 3, 4 subintervals. Then we'll need to know where each of these occur. Well, at the middle, it's at 3. But how about here? Let's see, well, 1.5 and 4.5. Okay. And we can imagine, okay, you know, the function is going to be somewhere above, it's a parabola, right? Somewhere above here. I don't have to actually draw it. Which of these numbers would I use to find the heights of my rectangles? And if I'm using R4, then that would be these. That's x1, x2, x3, and x4. At 1.5, 3, 4.5, and 6, right? The right sides of each region. So in order to find R4, here's all I got to do. Oh, you know what? I should note, what is delta x? The width of each rectangle is 1.5 here, right? If you wanted a way to find delta x, like to compute delta x, by the way, you could take the total distance. Here we'd go 6 minus 0 and divide it by the number of subintervals. So here 6 divided by 4 is the 1.5, the width of each one. Here's what I can do. I can say, okay, the height of my first rectangle is at 1.5. So I'd find the height by plugging that into the function. And then the width, I'd multiply by 1.5. So that's my first rectangle. My second rectangle, the height is at 3. But it's still got a width of 1.5. The third rectangle, the height is at 4.5. So f of 4.5 times 1.5. And finally, the fourth rectangle, the height occurs at 6. So f of 6 times 1.5. And I could crunch all these numbers and get it. Before I do that, there's a way that's just a little bit faster. Notice that each one gets multiplied by the 1.5, of course. So what if I factored that out? That would look like this. I'm essentially just adding up all of the heights of my 4 endpoints and then multiplying that by 1.5. Okay, So in the future, maybe we can skip this first step and just say, hey, all I got to do once I know where the heights occur, add up all the heights and multiply by that one width. It's like, because it would like distribute to all of them. All right. At this point, it's a little bit tedious, but that's how it is. When you start from the ground up, we got to find f of 1.5, f of 3, f of 4.5, f of 6. Remember our function back here. I recommend doing this all in one shot in your calculator. Don't do them one at a time and then, record them all. Just say, hey, 1.5 squared plus 1 plus 3 squared plus 1, right? And so on. So I got all of those heights to be 71.5, but then still multiply by 1.5. My final answer, 107.25, the approximation. Now, without the drawing, we're not sure if this is an over approximation or an under approximation. We don't really care. We're just trying to get R4. If we wanted to know if it was over or under, we should probably then, actually look at the graph. Okay, but not our concern right now. Okay. Part B. M5 or f of x equals x squared e to the negative x from 1 to 4. All right. I'm really glad I don't have to graph that for this one. I'm just going to create that number line from 1 to 4. And note how many subintervals there are. 5 of them. Okay, yeah. 5. It's tough to do by eye. Let's see. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Where do these occur? What's delta x? It's a little bit tougher when you're not starting at 0 and when it's something like 5. So I'm going to go over here. Delta x is 4 minus 1 over 5. So that's 3/5. That's 0.6. Okay, so this is going to be at 1.6, at 2.2, at 2.8, at 3.4, and then at 4. Perfect. But what I need is the midpoints. So I got to figure out where all these midpoints occur. That's where the heights of my rectangles will be. Well, let's see. If that's halfway between, that's at 1.3. The next one's at 1.9. The next one is at 2.5. You know what? Once you find the first one, then you can add that delta x, because that is that full width at that point. Add 0.6, add 0.6. This one would be 3.1. And finally 3.7. And yeah, that looks good. So that's our x1, x2, x3, x4, and x5. Okay. If we wanted to find M5, we'd say, all right, let's find the height at each of these midpoints and multiply it by the width. But of course, we could do that thing where we factor this out. Why don't we do f of 1.3 plus f of 1.9 plus f of 2.5 plus f of 3.1 plus f of 3.4. Oh, not 3.4, 3.7. Let's make sure I got them all. 1.3, 1.9, 2.5, 3.1, 3.7. That all gets multiplied by our width, 0.6. Okay. Oh boy. All right, so far so good, but now we got to plug each one into this. Okay, well, let's see here. 1.3 squared e to the negative 1.3 plus 1.9 squared e to the negative 1.9 plus 2.5 squared e to the negative 2.5 plus 3.1 squared e to the negative 3.1 plus 3.7 squared e to the negative 3.7. That's what I got for all those heights. I'm not going to write that down. Let's just multiply by 0.6. And I don't think that's correct. I think I messed up somewhere. Let me try that again. Is that right? If I get it again the second time, then I'll be happy. Plus 1.9 squared. Okay. Plus 2.5 squared. Plus 3.1 squared. E to the negative 3.1. Plus 3.7 squared. E to the negative 3.7. I got the same thing times 0.6. Okay. M5 doesn't tell us how to round. I'm gonna go to 3 decimal places. I don't know. I got 1.371. Looks pretty good. Hopefully that's correct. And there you go. Hey, so you might be thinking like, what's the biggest, number of subintervals we might see in the homework? You might get some rather large ones. I wouldn't be surprised if some of them have you do like even up to 10 or even 12. Occasionally, most of the time we stick to things around these numbers 4, 5, 6, 8, maybe. But I think you do get some that are a little bit higher up there. Now, kind of one thing to reflect on, obviously we got our answers here, but something to reflect on. If we wanted to be more accurate, how could we do that? So like if I found M5 and I got my answer, but I want to say, you know what, maybe I could be more accurate than this. How might I do that? Well, if I take more subintervals, then that's going to be more accurate, right? Like if I found M10, then now each rectangle is more narrow, and so it has less error where it's either leaving a gap or an overhang, right? And so more subintervals will reduce the amount of error each time. So if it's asking for like something like, an M8 or M10 or 12 even, those are going to be quite a bit more accurate than 4, 3 subintervals or 4 subintervals. But you go about the same way, just, it's got more numbers to calculate. Okay, let's stop this video here. We'll do one more example in the next one.